Alors, j'ai pas de retour, mais on me dit que c'est bon. Donc, vous êtes derrière votre écran. Je suis Madeleine Martins. Je suis membre du comité exécutif de SKEMA, responsable de la relation avec les diplômés, surtout aujourd'hui responsable de SKEMA Canada. Je suis particulièrement fière de vous accueillir pour cette première classe de maître en direct du Centre de ressources et de recherche en intelligence artificielle depuis Montréal. It's the reason why I'm starting in French, but as we are talking to everybody all around the SKEMA world and in each campus, the rest of the allocation and the conference will take place in English. I'm very proud to host you today. And first of all, I will give the microphone. I don't know, Margarita, if you are there, but the goal is to introduce Margherita Pagani, who is a scientific director of the SKEMA AI School for Business. Are you in Paris, Margherita?
Yes, I am. Hello, Madeleine.
Let's go.
Okay. So thank you very much, Madeleine, and a big thank you to Ali Amami, who is the professor joining us for the first masterclass, and a special thank also to René Garcia, who is the scientific director of Montreal Resource and Resource Center. There is a big echo. Okay, now it's corrected. So I just wanted to spend 2 words to introduce this first masterclass that has been realized inside the SKEMA School for Business with the Montreal Resource Research Center, which is one of the most important promising element of SKEMA for the development of AI. This masterclass is the first of a series, and the goal of the series is to cover the main technical topics related to AI, addressing social scientists, addressing faculty, executives, and students to introduce them to the basic technical topics related to AI. There is a philosophy inside this action, which is the Masterclass series, because we'll try to cover the performances, so how AI follows the performances that AI tries to solve. So we cover cognition, language, vision, motion, collaboration. So that's all. I thank Ali and Amami for joining. Maybe René will introduce him more in detail.
Good day to all participants around the world for this first masterclass on natural language processing. So let me say a few words about the Montreal AI Research and Resource Center. We are both a research center with experts in AI, and also we are a resource center to prepare experience and executive programs for the rest of the schools, for all of SKEMA Business School. So we chose Montreal because of its ecosystem in artificial intelligence and to benefit from it, and also to bring to Montreal the international network of partners that SKEMA Business School has around the world. So let me introduce our speaker today, Professor Ali Amami. He's an assistant professor at Brock University in Ontario, Canada, and he's also an adjunct professor with SKEMA Canada. He holds a PhD in computer science from McGill University and the Mila Center in Montreal. He has developed a pioneering system in machine learning to better understand natural language, and he has applied his innovative research to various sectors, namely or including transportation, healthcare, robotics, games, finance, and conversational agents. So without further ado, let's hear what Ali Amami has to say on generalizable, ethical, interpretable natural language processing, science or science fiction. Ali?
Just confirming again, can you hear me, Margarita? Perfect. Thank you so much, Renee. And thank you, everybody, for attending, both in person and virtually. So good morning in person, and I guess in Paris, good afternoon, or wherever you are, good evening, potentially. It was a mouthful of a title, yeah, so thank you for that. Today, I really want to give you guys all the latest scoop and really the buzz about this field that really has taken the world by storm, natural language processing, and do a little bit more of just having a hand-wavy explanation of really the three desiderata of what makes natural language processing potentially the difference between what we see today versus what we can imagine would be a real live talking conversant agent that can really speak with us and just about really understand language. So what I want to do is start with a background on natural language processing and then do a deep dive and really fast forward to today, what the real problems we're facing as a community are and what are some of the things that we're doing to solve them. And hopefully maybe this would lead to a really nice discussion at the very end, pending time, on whether or not we can really answer that question. Is it really science or is it just the stuff of dreams? So as we just experienced, even from the short introductions we had, and this issue with getting things to work, language is not just everywhere, but it's extremely important. And what's interesting about language is that the levels of formality can vary quite drastically. You could be expressing language in very formal texts, like Shakespeare or poetry, and it could be through text messages and be very informal. And another interesting thing with language, so far as we know, it seems to be the defining trait of what it means to be human. It looks like from the studies that we're having, yes, there are animals and there are species that are very primitive that can express things with language, but it seems to be just signals. It only seems to be us humans that are able to have what we call designators, which are words that don't actually have any mapping to the actual meaning, like cat, and yet everybody understands what it means. What's also very human to do is to try to mimic what we see in nature. So now naturally the idea of trying to mimic language becomes the task of natural language processing. Can we create something that can understand language as well as humans do? And this developed really into a successful field, so successful that it seems to be really on the rise, especially as of the last few years. I did a little bit of a cursory analysis of how it has been growing in the last few years, and it's surprising to see that investments on various fronts in the technological industry are increasing from at least 10% annually to nearly doubling in the last few years. According to another source, I found that the global NLP industry is also expected to reach to US $42 billion in just the next 2 or 3 years, in contrast to the $10.9 billion that it was in 2021. Another source has a graph that it expressed the sources for where NLP is directed towards, software, service, and hardware, and we see almost like a Moore's law, or like an exponential climb of the investments in NLP. So there's quite a bit of interest in this field of natural language processing. But before I go on, we should really have a more precise understanding of what natural language processing actually is. So there are really 3 terms, the 3 words that really pivot and create this idea of natural language processing. The first one is natural language. So what is natural language? Natural language, it's a little bit of a subtlety, the difference between natural language and just language as a whole. So these are languages that are evolving naturally over time. So like English or French, these are spoken languages that don't necessarily have a purpose, and they're evolving through vocal or oral use, as opposed to, let's say, a language that was designed for a specific purpose, like let's say a programming language like Python. And the domains of natural language can also vary quite a bit. Also, the units of natural language, we don't just think of it as words, we can think of it as just acoustic signals, so sounds, parts of words, which are called phonemes, words themselves, the structure of words, which is syntax, or semantics, or the meaning of words. And of course, we can express words in different forms, so we can have it in terms of speech or text. Now, there's 2 ways we can really process natural language. Either we're trying to understand the natural language that someone's expressing to us, and this is a big field in natural language processing. So on the right, you see the bubble that kind of expresses the 2 major fields within natural language processing. So one of them is natural language understanding, and this is most of real natural language processing work is this, but also recently natural language generation. So this is the idea of actually producing language is gaining popularity as well. And we've seen this in terms of, let's say, machine translation. Now, the next pivot point is what we mean by modeling, when we say we're modeling natural language. So here we're really talking about goals, and goals can vary from different levels. The first goal of natural language processing is honestly just NLP for the sake of NLP. What can we do that mimics human behavior? For example, can we make a system summarize a text the way that we summarize, answer questions the way we answer questions? Then there's a larger goal of like artificial intelligence. Can we really come up with a system or a robot that can at least look like, and we're going to discuss this a little bit later, but at least look like it has human intelligence? Another really interesting flip side of natural language processing is actually computational linguistics. And I've noticed this, it's almost a philosophical reality. Sometimes in trying to recreate something, you'll learn about that phenomenon itself. So sometimes you'll actually use natural language processing to learn about language altogether. So it's a bit of an ironic truth. So in general, the projects that come out of natural language processing can vary in terms of their application, and they can be just for entertainment purposes or be as big as influencing a financial sector. On the right, if you can kind of see that graphic, it's one of the latest deep learning models that is outperforming a human on trivia questions. So for example, which 20th century British Prime Minister was born to Portsmouth? The human got it wrong, but T5, which was the deep learning model, got it right. And the final part about natural language processing, computational models and techniques, this is really just how we do it. And I really want to, and you'll see soon, give you a brief kind of timeline of how we have evolved these methods over the last really 50 or 60 years in developing better and better systems that at least seem more capable of having natural language abilities. So these methods really vary in terms of how we first gather the data that these models need to learn from, to how we actually test to see how well these models are doing, and then how the models are actually training on the data. So there's many different methods that are used there. And we should never forget rule-based methods also exist, and they tend to also be very competitive too. And we'll look at that later. And this graphic is the classical graphic of like where natural language processing falls in this grand field of AI. You can see it's one of the projects of AI. So it's within AI, and then it's very important to always remember, because we often forget lately, that natural language processing is much more than just machine learning, which is ML or deep learning. One of the techniques of natural language processing is machine learning as of late, under which there's also deep learning. And today we're going to have an appreciation of why deep learning seems to work, but also why it seems to have been failing as of late. So as I mentioned, there are different tasks that we can accomplish with natural language processing. Mainly in the NLP community, there are core tasks that we have been really entertaining ourselves with. For example, just text classification, extracting information from corpora, conversational agents. But each of these really has a corresponding application in the real world. So for example, if you do text classification really well, then you can apply that and do spam classification potentially well. Or information extraction can help you with calendar event extraction. Even furthermore, you can take this to the industry level and do things like social media analysis, retail catalog extraction, health records analysis, and what we've been working on, for example, financial analysis. And we'll look at some of that. Speaking of which, what's interesting is that since we're all really interested in the applications of AI in finance and business, I really was interested in seeing how natural language processing has been perceived and used as of late in business disciplines. So I actually came across a really nice literature review where they were looking at the use of natural language processing techniques in business disciplines according to where they were in business journals. And they found, as you can see, quite a bit of an exponential rise in terms of the use of natural language processing on various papers through various business discipline journals. And the pie chart on the right kind of divides, I don't know if you can see it clearly, but in general, you can see, for example, in management, which is the big blue part, there's been quite a bit of natural language processing work, and marketing science, which is orange, and there's been just a varied distribution of its use in business disciplines. But this was up to 2019, so I was personally curious extending it, so I did a little bit of a deep dive myself, and I found that it continued indeed with this exponential rise, and as of 2021, we are seeing more and more of the use of natural language processing in business disciplines. So just to give you a bit of a briefer of how it has been used in business, for example, in accounting, we've seen applications being using text in 10K filings. So these are reports of firms, and we can really use automatic methods and machine learning methods to predict firms' performance metrics like the firm's future value. We can look at customer attitudes and behaviors on social media in terms of their perception of a product in order to actually predict a firm's performance, because it turns out that their perception affects other customers' behaviors and in fact may even influence investors' behaviors as well. So there's been a lot of use of that. Conference call topic modeling as well, to model conference calls according to certain categories. I was interested in seeing the approaches used in some of these. In general, it looks like they have been using supervised learning, so that was a method that kind of preceded, or they never really delved into deep learning methods, and they used something called latent Dirichlet analysis and sentiment analysis as well. So it looks like deep learning hasn't really taken over accounting yet, so there's a huge opportunity there. It's ironic that we're talking about AI and we really just can't get a simple projector to work. Okay, so let's continue. So in finance, I found that the applications varied as well quite a bit. I've seen work on predicting the effect of news, so the articles in the news in terms of tone, the sentiment, so like the feeling that they possessed, and unusualness of word flow on the reaction of the market. And then there's some work on investigating the differences of this exact effect at the country level versus between developed and emerging markets, which is really interesting. Also with this, I didn't see too much deep learning work. I saw some sentiment analysis and a lot of work on databases. There was actually a lot of complaints I've seen in the literature about how the lexicon or the databases developed for evaluating sentiment was specific to the fields of psychology and not in finance. So they're asking for the community to start to develop maybe keywords that express financial sentiments and tones. So there's a lot of opportunities there as well. In marketing is where I've actually seen some deep learning work. And one of those is to use the behavior of customers in terms of how they think of a product's, let's say, price or quality or service to forecast future sales, and as well to look at just shopping experience of customers. So it seems like when it comes to marketing, there has been a lot of work in deep learning. So opportunities there will really also be opportunities we talk about in terms of the three major problems of deep learning, which hopefully will be the topic that we're going to cover in depth today. What I really want to do with this slide is not go into it in depth, but there's a lesson to be learned about the timeline or the story of NLP. And unfortunately, I think it's a lesson that we haven't really learned in all of science, and that's that we can learn a lot from the past, and history usually repeats itself. So a lot of things that we didn't remember in the pre-deep learning era, so this is between the 1940s to 1990s, is really repeating itself today. And the long story short was when we began with 1949, our interest was in machine translation. And it was actually for translating Russian to English and English to Russian. As you can imagine, in that time, it was really, really important. Funny that maybe that's starting to repeat itself as well. But that actually inspired a lot of interest in NLP work. And then really we saw a real increase in popularity of NLP, or natural language processing methods, as early as the 1940s. And we had a little bit of a hype around NLP at that time as well. What ended up happening in the early 1950s was we saw that it was actually very difficult to translate text, and it was very, very expensive. And in fact, there was an advisory committee called ALPAC that actually demanded that we stop funding NLP altogether. Then in the 1960s, thanks to Chomsky, that basically there was this rebirth of NLP, and there was excitement that maybe we could actually generalize NLP. So they were actually suffering from some issues of generalizability, which we'll talk about. Then there was an explosion of work in NLP, and then we eventually reached the deep learning era, where we started getting models that seem to behave really, really well. They seem to be performing quite well. And now we're going to fast forward into 2022, where we're seeing there's a little bit of an issue that we're having, like we were having in 1949, and I want to talk about those later. What I had on the left slide, and you may not be able to see, left side, which you may not be able to see really clearly, is really nice because it shows that some of the work that was done in the early 1960s, for example, was still quite interesting. There was a little chat that was actually going on between two chatbots, which one of them was a famous Eliza. So it's like almost a psychiatrist chatbot between Perry, and Perry was actually a chatbot that was designed to seem manic schizophrenic. And it was a very funny conversation they ended up having. You can pit two chatbots together. Deep learning era, you also have very interesting chatbots as well. There's a chatbot called Yi, who was based off of Kanye West's alter ego. So he was trained on Kanye West's text and conversations. And I played around with it. It actually does a pretty good job of capturing Kanye West's kind of nature. But there's a lot of good work that was done between the 1940s until now, and it's hard to say what was better and what was worse. So that was really the lesson there. So as of 2018 to present, the real trend that we've been seeing is that we have really converged as a community on these methods, on these models called deep learning models. And I'll give you a brief overview of what those are. But in short, what I want to show you here is that these deep learning models that are doing better and better on what looks like natural language processing tasks are also getting larger and larger. So in this graph, what I'm showing you is the name of a bunch of really popular recent deep learning models. And on the y-axis, we see their size in terms of billions of parameters. And I'll give you a sense of what it means to have a billion parameters. But in like something like 2019, we had a model called GPT-3, which everybody was very excited about. And what's very interesting is that something like 2019 is really ancient era when it comes to NLP talk. So even every time I'm preparing a presentation, I have to scour the literature and find updates to even something like GPT-3. If I mentioned GPT-3 in an NLP conference today, they'd laugh at me and consider me archaic. So the next models that actually completely displaced GPT-3 are Gopher of 2020, which was developed by DeepMind, Megatron, which NVIDIA topped in 2020 as well, and then Palm. So this is Pathways Language Model of 2022 by Google. And they really are just beyond the graph. So in terms of billions of parameters, they're really just almost reaching trillion. So in the case of Palm, it's actually 540 billion parameters, and it's 3 times as large as GPT-3. And when GPT-3 came out, it was 10-folds larger than the previous language models. Now, what I want to give you a sense of here is where Palm stands to all the other when I say language model, I mean deep learning models capable technically of language in terms of the number of computations it took to train this model. So on the y-axis is petaflops. A petaflop is a quadrillion flops. So this is, I believe it's 1,000 million billion, if I see a nod in the room, 1,000 million billion flops. So flops are floating point operations. So these are just quick computations, and there's 2.5 billion petaflops of those that took Palm to where it's at right now, which if you want to get a sense of time and compute, it took around 60-something days on a ton of very, very powerful computers to train this. And it was around a budget of $15 million. And the previous model of, I think, Gopher of 2020 was 10 million, to give you a sense. So we're spending a lot of resources right now on these models, hopefully wanting from them to do something really well. And these are some of the expectations we have from them. So as these models are growing, it looks like at least they're doing more and more. So they're going from, let's say, just question answering to doing arithmetic, summarization, code completion, translation, common sense reasoning, which is my pet topic, and more. And they've been really dominating, it seems like, on at least some of the data sets that have been developed in the natural language processing community. So on this graph, we see the performance of these models over the last few years on a benchmark called superglue. And superglue is just this natural language processing benchmark that is pitting models against really difficult questions and seeing if they can do well on that and the performance rises, they seem to be more capable of language. That blue line on the top is human performance on superglue. It looks like as of 2021, these models are actually surpassing human performance. So let's actually qualitatively look at some of the things that they're doing. So let's read, I'm going to read you this text. So this is an input that we've given that really powerful 540 billion parameter model and see how it continues the text. So this task is called task sentence completion, or we are just basically having an output based on a context and seeing how it completes essentially the thoughts. Here it says, Jennifer looked out her window and sees a really cool cloud below her. She unbuckles her seatbelt and heads to the bathroom. is Jennifer probably traveling more than 300 miles per hour relative to the Earth? The output was 300 miles per hour is about 480 kilometers per hour. This is about the speed of a commercial plane. Clouds are usually below airplanes, so Jennifer is probably on an airplane. The answer is yes. We're immediately very impressed by this. I mean, and this is actually released by Google itself, so it seems to excite us. Maybe the $15 million was worth it, and all those hours of compute was also worth it. Which, by the way, just training one of these models is, and I don't want to botch exactly the approximation, but something like a transatlantic flight in terms of energy was used to train something like this. However, with all that looks really nice with, I can always show you something else. So what if I give it this prompt? The cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? And I know it's early morning for some of us, so maybe some of us wouldn't even be able to get that well, but the model was wrong to say that the answer is 50. Now, I guess, you know, sometimes we think maybe we're expecting too much of a model, right? Humans can also make mistakes, right? So let's actually look at really what might bug us about some of these really large models. So let's actually make things a little bit more simple. Let's look at how GPT-3, so mind you, GPT-3, although it was 2-3 years ago, was extremely powerful as well. If we gave it a sentence like this and I give it the task of sentiment analysis, so all I want it to do is to tell me, does this sound like the person who said it was saying something positive or was saying something negative, okay? So if I said I would rate 4 stars out of 5, let's say of a restaurant that I went to, it correctly predicted that that meant positive. Now, I don't care how early in the morning it is, but if I changed this to I would rate 4 stars out of 10 for all of us, we would probably get this correctly and say that the sentiment is negative. But actually, something as powerful as GPT-3 would get completely broken by this and say still positive. And that was wrong. And so this is the famous problem of generalizability. And this is what we talk a lot in the community about. These models seem like they just don't generalize. They'll do really well on a number of instances that come from a data set. So for example, this I would rate 4 stars out of 5 was straight from a data set, but then when we humans test these models out in the real world, change the instance a little bit, while we humans wouldn't be really disturbed by these changes, these models really, really are. So they seem not to be able to generalize. And if I said something like I would rate 8 stars out of 10, so instead of 4 stars out of 10, 8 stars out of 10, and it's positive, the next question is, and the next thing I want to talk about is, if I asked you guys why, you might be able to give me a sense of why that is, because 8 out of 10 is 80%. Now, when it comes to asking a model why, it's very difficult, and we'll talk about this, but the closest we can get is something like an image like this, where it can show you the weight of how much it finds relevant words in that sentence in terms of its output. So let's say the model actually said positive, and it gave you something like this, like I really cared the fact that it was 8, but it really didn't care that it was out of 10. So it kind of makes you confused about how it actually reasoned about it. So now we have a problem of interpretability. When a model is correct, we're not even exactly sure why it was correct either. So this is a real big problem in the NLP community as well. Finally, to make matters worse, we have a real pressing problem, and that's really being uncovered in the last few years, and that's the problem of ethics. So let me read for you verbatim a text that was from a conclusion of a paper in 2016. All 4 classifiers perform consistently well and produce evidence for the validity of automated face-induced inference on criminality. So what they're doing is they're trying to predict criminality by looking just at faces of people. Also, we find some discriminating structural features for predicting criminality, such as lip curvature, eye inner corner distance, and the so-called nose-mouth angle. So they found ways of interpreting how someone can be in terms of their tendency to be a criminal just based on their features, and they tended to do well on a data set. And that was for a vision. For natural language processing, similar problems arise. There was actually an algorithm called Optum in 2019 that was used on over 200 million people in the US to predict if they needed extra medical care, and it turns out that it heavily favored white patients over black ones. Black patients who were just as sick weren't recommended to having extra medical care, just based off of the text that implied, let's say, their wages and the cost of medical care that was induced by them. It ended up being extremely biased towards favoring the white community. So these are some serious problems, and this is the problem of ethics. So really, I could summarize the 3 issues of the natural language processing world in terms of these 3 desert data that if we don't overcome, we can't make that next leap into successful natural language processing systems. So the goal of today's masterclass is to do a brief overview of some of these issues and also talk about some of the work that I'm doing and the community is doing as well in order to address these. And really, potentially at the very end of the masterclass, to be able to discuss, is it even possible to overcome these from what we've seen, or is this maybe particularly what makes us human and robots robots? Before we do that, I think something that I really am starting to push for the community to remember is that the general goal or the purpose of artificial intelligence, sometimes we really get lost in a kind of tunnel vision of a project that we're doing, and we're missing out on the overall picture of the general goal of AI. In fact, in my thesis, I was emphasizing this in one of my chapters because it's really important to remind yourself what's the purpose of natural language processing underneath this umbrella of artificial intelligence. So it turns out a lot of philosophers had a lot to say about this. When we just say artificial intelligence, there's a lot of ambiguities already because the idea of something being artificial is quite ambiguous. Do we mean that it's artificially produced so that the intelligence part is real, or that the intelligence is actually artificial itself? So did we create it in an artificial way, or do we create the real thing, but that in an artificial way? And that leads to 2 kind of camps. There's 2 cults essentially in the field. One of them believes that as long as something looks like it's intelligent, it's just as good as intelligent, right? And that actually developed into the Turing Test, basically being the test that if you can fool a human to looking like you're intelligent, then you're just as intelligent as you need to be, right? And that's actually where the terms weak AI and strong AI come from, where weak AI is just the project of trying to make something look intelligent, versus strong AI, we're trying to make something actually truly intelligent. And the other camp is functionalism, where they're saying there actually is a difference between intelligence and the behavior that looks intelligent. And within that, there's a camp called computational functionalism, where they believe that that mental part, the intelligence, we can actually compute that. We can actually produce that. So this debate is something really, really important to remember as we're going to be speaking today and discussing this, because you have to decide from the get-go, which camp are you in? Are you in the behaviorism camp, which concedes that it's okay to just look intelligent, and in that case you've achieved AI? Or is it more important to actually be intelligent? And there's a difference between the 2. So let's look at the generalizability problem. I really, really like this graph because what it's doing is it's showing the progress of deep learning systems on various tasks that we've given them since the 2000s to 2020. For example, the blue bar is the performance of deep learning systems on a popular task called MNIST, which is like a vision task or a handwritten digit recognition task. And then we have other tasks that are developed over the years, but something really odd is happening. And it looks like as we're progressing through the years, it's getting easier and easier to do better and better on these tasks. So actually the numbers on the y-axis are normalized. So 0 means human performance. If you're below 0, you're doing worse than human. And if you're above, you're doing better. So it looks like as we're progressing over time, it's getting easier and easier to do better than human performance really, really quickly on any task that we give these deep learning models. But as I've shown you in generalizability, it seems that although they're doing really easy, well on these tasks, and I'll show you guys what I mean by a task, it's very easy to break these models by just changing a task instance just a little bit. For example, on another sentiment analysis task, if I gave it the sentence, "There is no pleasure in watching a child suffer," these deep learning models tend to do well on that. They'll say the prediction is negative. So it's not a positive sentiment. But then if I just change the words up, the wording. So there was a really nice work by Ear in 2018 where they said, I'm not even going to add another word. I'm just going to change the wording of a sentence to change the sentiment. And if you said, in watching the child suffer, there is no pleasure. And the prediction here was positive, which also shows the brittleness of these models. So there's something funny about this, and and I actually took this from a paper that was paraphrasing something from Shakespeare that says there's something rotten essentially in the state of the art. So when someone comes up with the state of the art model, there might be something just behind that. And the problem there is generalizability. It looks like as they're doing better and better on these tasks, they're doing worse and worse in deployment. So there are some potential solutions that are being proposed in the community as of the last few years, and I'm going to briefly overview them in terms of how easy it is to actually accomplish these. So the first one is counterfactual data augmentation. We'll talk about that. The other one is to actually come up with new tasks, like devise new benchmarks. And finally, the one that I'm really excited about that I'm working on is revolutionizing just this static benchmark setup. So the first idea of counterfactual data augmentation is sort of what you've already seen. So it's what you're doing is you're getting a bunch of instances, like for example, in the bottom we see the world of Atlantis hidden beneath the Earth's core is fantastic. So the sentiment there is positive. Then what you're doing is you're asking a human to try to change the wording of that a little bit to change the correct label and challenge models and then iterate that process to create a new data set. So that's called counterfactual data augmentation. So in this case, we had a human change that sentence to the world of Atlantis hidden beneath the Earth's core is supposed to be fantastic, right? And that addition actually, it triggers what is called sarcasm. So sarcastically, if you're saying it's supposed to be fantastic, it's negative. So you're now creating a new data set to give these models to train on so they can learn on these instances, so maybe they'll be less brittle in the real world. So that's counterfactual data augmentation. And there's a lot of really recent work on that, both for sentiment analysis like I've shown you, and other tasks as well, like natural language inference as of the last year. And it shows to be improving results. So we actually seem to have the result that when you are giving a model an original data set, it performs at a certain accuracy, let's say in a bunch of tasks. So SVM, naive Bayes, Elmo, these are all just models. When they're training on an original data set, their performance seems to be as is. So like let's say 87% for SVM, 84 for naive Bayes. And let's say for these models, like BERT is one of, it's a powerful deep learning model, is doing something like 88%. But when you're giving it also the revised data set, which is like the augmented data that the humans are giving it, their performance increases on both the original data set and the augmented data set. All to say, they seem to be getting less brittle. However, there's an issue with this as well. And this is one that we're only coming across now. And that's, there's a dustpan line effect. So sure, maybe you can train a model to start to do well on this instance of the world of Atlantis hidden beneath the Earth's core is supposed to be fantastic. But then a human didn't actually add more to that, potentially, like something like the world of Atlantis hidden beneath the Earth's core is supposed to be boring. And that actually flips the sentiment to maybe positive because you're being sarcastic about that. So how much do we have to keep augmenting these data sets until these models achieve what we want? It looks like it's endless. So sort of dustpan line effect. And so the next I guess the next logical conclusion is maybe we just need to be building different tasks, like come up with different challenging tasks to give to these models. So this is something like what I did in 2020. I'm just giving these models these sentences and I'm asking them to rate them in terms of plausibility. For example, I'll say something like a monkey turns on a light switch, and then give the model a sentence like a dead monkey turns on a light switch and ask what the change in probability it should be. So a human would say a dead monkey turning on a light switch should be impossible. Or let's say a leaf falls from a tree in autumn. A dead leaf falls from a tree in autumn actually is more likely. You can see how that's challenging because a model might think that making something dead would make it impossible in doing anything, but not all the time. So a dead leaf falling from a tree in autumn actually is more likely. So this is an interesting, challenging task. And I want to just, I don't want to go too much into the details of this, but it turns out that it is very nuanced and actually fixing a context and changing that adjective as well can challenge models. And it looks like humans do really, really well on this task, but models, even these powerful deep learning models, do poorly. For example, we see on the left, humans are doing something like 85% on this task, and models are doing much worse. Qualitative glimpses are always really nice. So it looks like, for example, some of the instances are easy for the model, some of them are hard. For example, I saw that when you gave a sentence, bananas are yellow, and then you added yellow bananas are yellow, the humans say that's necessarily true, but the model says that it's equally likely. So we see that models are challenged with certain instances more than humans. But the reason I went by that really, really quickly is because I've immediately realized as of 2020 that that's still problematic, because there's still limitations of just constantly coming up with new tasks. Number one, the first one is, look, we're coming up with these data sets, like we're coming up with these sentences that we're feeding to these models, right? But when we're deploying the model in the real world, and what are some of the real world qualities of data that we're seeing or language? For example, there's typos, there's informalisms, there's ups and downs with the way that people treat models. Like, I don't know if you've seen, like, I went to a conference once, it was the creators and developers of Amazon and Google Home, and they realized that 80% of the interactions humans have right now is actually profanities at the Google Home because they can't get it to work. And they have to censor it all. And it looks like humans don't behave the same way towards robots in the real world than we have them being given in these data sets. Also, humans tend to be very adversarial. They tend to try to trick models and challenge models. These data sets seem to be too optimistic, it seems. Another big problem with data sets or benchmarks is that they're stale. So, for example, in 2022, I went to a conference where they made a really good point. If you asked even Google Home, when were the last Olympics, they would tell you Beijing, for example. But if the next Olympics happen, unless that model trained on a new data set, it would continue to tell you Beijing. So the staleness of data is a huge problem. And as these models are getting bigger and bigger, if you're requiring them to retrain on large data, we're wasting so much time and so much effort to constantly update these. Whereas a human, how quickly would a human update itself to know that the next Olympics that happen, it'll just update the answer, but not its procedure to answering that. And then the other problem is that there's only so many possible benchmarks. So I scratched my head until I can find one benchmark that was new, but how many more do we have until we reach a limit or a glass ceiling where we just can't train new models on new benchmarks? Finally, something I personally encountered was labels are very difficult to have high quality. You can give a huge number of instances to crowd workers, but unfortunately we're not realizing in the natural language processing community, there's nobody that actually opens up the data set and sees how that labeling was done. And oftentimes those annotators are really just trying to make quick money, and they're labeling it very poorly. So to actually do a really good job at labeling takes extreme effort as well, and I've been seeing some of that. For example, in 2022, I saw that there was actually a statistical fix to inter-rater reliability, which apparently reliability of data actually is a completely different paradigm when you're dealing with crowdsourced data. And finally, it's actually hard to keep track of benchmarks. We can come up with thousands of benchmarks, but how do you get the entire community to learn about one and to actually use one? For example, for machine translation, although there are actually 108 ways or metrics of looking at how high quality a translation is, everybody just kind of has a sheep-like mentality of following one thing that they've liked. So it really is hard to push the community to taking on a new benchmark. For example, I came up with a few benchmarks. I found that some of them happened to become popular and some of them didn't. So this one so far hasn't had as much work as some of the other benchmarks that I proposed. So it's very difficult to actually round up a community to working on a benchmark. And finally, back to that debate about weak AI and strong AI, the question should be asked, if these models are doing well on these data sets, are they behaving intelligently or are they actually intelligent? So this seems to be the problem. And what I have on the right here is a kind of dog chasing its own tail kind of thing. Because as we're solving these data sets, we're coming up with new data sets, seeing that they have problems, coming up with new ones, and it seems like we're just going round and round. So this seems to be a huge problem. The new idea that's really taking the NLP world by storm, and it actually I really do, and I am optimistic about it, is never-ending learning, or human in the loop as well. And so as of 2020, what seems like it might work is if we actually remember that the idea is for them to mimic humans and to actually constantly have a human in the loop of their training. So the idea here would be, we first have a human write an example. For example, the human would be given the sentence, Kevin yelled at Jim, and the label definitely correct. They have to try to come up with a continuation to that matches the label. So if Kevin yelled at Jim, Kevin must have been angry. So the human writes Kevin was angry. Now the human feeds this to the model, and the model makes a prediction on this sentence. And the model doesn't see the label definitely correct. Now if the model was right to say definitely correct, this sentence gets sent to the training data set, and if it was wrong, it gets sent to the development or test set. And then what you end up doing, and if it was wrong, it meant that the human successfully fooled the model. And what you then do is, if it successfully fooled the model, you can just have a quality check of having other humans verify that that label was completely correct. But the key part here is that then you repeat this iteratively. And the new model that's trained on that data set is now pitted against another human constantly and constantly and constantly until these models are just growing. But the point is that the data set isn't stale. What I vision and my dream is that, imagine you can tune in to a website and you are faced against the model and you give a data set, you give a sentence to the model, it'll say that the model got it correct or incorrect. If it got it correct, well, that's great. That's added to the model's instances that it got correct. But if it got it incorrect, the model learns from you. And it's constantly having this interface back and forth with humans. So I gave an example, and I'm starting to work with the student on this. So I'm not going to go into the details of this because I believe we want to have a little bit more time for questions. But I'm developing it for a data set that I really like, which is common sense reasoning. And basically what I'm showing here is that if the model gets sentences incorrect, there's nothing to worry about. If the model gets it correctly, then it adds it to the instances. I only have 5 minutes? Okay. All right, so I'm going to fast forward here. Preliminary observations about this is that it's really, really nice because, as I mentioned, the human adversary that we're seeing in the real world is brought into the loop. We're having humans which are adversarial be what the model's learning from, as opposed to giving them sentences that we're just scraping from the web, which are often really, really simplified. The question, however, of why a model is doing well is still beyond us. And that's, why is it, for example, a model would get a certain sentence incorrectly and would it get another sentence correctly? Okay, so that yields itself to the interpretability problem. So the interpretability problem is actually really one of the most philosophical problems in AI altogether. And I really want, and I think I'm being cut for time. I think maybe that was part of the technical difficulties that really, because I was planning on 10 more minutes? Okay. So I don't know if I'll reach the ethical problem, but this really is my favorite topic here, interpretability, because it's such a buzzword in the field. Everybody wants to talk about interpretable models, but nobody wants to delve deep into what it actually means to be interpretable and what can it provide if something actually is interpretable. So I really want to address 3 important questions to have us really be in the picture of like this discussion of interpretability. Number 1, what does it actually mean to say something is interpretable? Number 2, if it really turns out that an uninterpretable model can't provide understanding, and I'll talk about what I mean by understanding, should they be used and in which cases? Finally, if they can provide some sort of understanding, what are some techniques we can use to actually understand these models? So some of the literature review I did on this term interpretable led to some of these definitions. One person said, so Rudin in 2018 said, a model is interpretable when we understand how all the variables in the model are jointly related to each other. I don't really like that definition so much because it's almost circular, because it's basically relying on our understanding of the word understand. So I'll have to get a little bit deeper about that. But I like the second one a little bit more. It says, a model is interpretable when we have the ability to explain it or present in understandable terms to a human the model's decision process. So I want to paraphrase what these two are basically saying, and it's essentially saying a model is interpretable when we have some idea of how the outputs are generated from the inputs. And basically from that we can offer an explanation to just anybody on how it did that. And what I mean by explanation is that maybe we can present either text or visual artifacts to show us the relationship between the input and the output of a model. But let me give you an example. So let's say I want to predict the expected salary of a worker according to years of education, so that's like X2, and work experience in terms of years. And I had this equation to predict it. Now, if I told you that W1, so if I trained the model that learned W1 and W2, and it told you that W1 was 200, can you explain to me what this means in terms of expected salary of work? This becomes easy because I can tell you for every unit increase of W1, so if W1 is 1, that means that we'll have $200 more for the expected salary. That right there was an explanation that just about anybody could understand. But what if I did a deep learning analog of this? So what I did was, let's say I still had Z, so that's the expected salary, and I had the variables as always, so I had X1, X2. Let's say I had more variables and more weights. Now I fed this Z into a non-linear function. And all you have to know by this is that it is this like funky function right here that outputted something that looks like it's a math equation, so it's a math term, but something that we really don't necessarily have a way of explaining really well. So in other words, what if I asked, what does it mean in this case if I told you W1 is 200? Turns out we really can't really answer that. I do know we have discussions, and someone amongst the audience is actually really good at explaining such things. So if I asked, like, for example, Sem, what this meant, you might be able to provide for me some sort of explanation, but what gets tougher and tougher for Sem potentially is if we're increasing the layers, we're increasing the number of times this output gets fed to another output, which gets fed to another output, which is essentially what deep learning models are. Just a bunch of these layers that are combined together. So we really lost the sense of what W1 actually meant to be 200. And we can't really explain that, even though it'll do very well on predicting the exact salary of that worker. So then we have to remind ourselves, wait, why black box models again? Well, because they're doing better. They're doing better and better at actually predicting these things that we want to predict. And they also do something very critical, and that's that they don't demand for us to do something called feature design. We can just feed them a bunch of inputs, so we can literally just give them a bunch of X1, X2, X3. Don't hand design these with any domain-specific knowledge, and it will find the correct combinations of dealing with these inputs to make an output. So it actually makes our job a little bit easier. And so this is kind of like the classical pipeline on the top. When you don't need deep learning models, there's a lot more work you have to do. But with deep learning, you don't have to do much. You rely on the deep learning model to figure it all out. Now, the criticism, though, is that they're not providing understanding. And understanding here, according to certain philosophers, is really just to be able to produce explanations as opposed to just knowing why. Right? Like in a math exam, if someone asked you, why did you get that answer? It's not enough to say, I understand it because I just know it. You have to provide an explanation that digs a bit deeper. Now, one thing to know is that when you say understanding, there's two things you can understand. You can either understand the model itself or the phenomenon that it's describing. We're really interested on the latter. We're really interested in knowing the phenomenon. So the question that should be asked here about interpretability is, does the fact that we cannot interpret highly complex models like what I show you, which in turn means that we cannot understand how they work, does that mean we can't understand the phenomenon that they predict? And that is the key problem of interpretability. Now, there's different answers to this. In one sense, you can say, what if we really don't even need an explanation, right? For example, if a calculator finds the result of a square root, we don't really care to know how it got that. We can just verify that it got it, right? But in other cases, it's actually critical. So we saw, like with criminality inference, you really want to know why a model will think someone is a criminal versus someone isn't. So there's ethical underpinnings, as well practical ones. So for healthcare, the doctor would indeed want to know exactly why the model, let's say, predicted a certain diagnosis so they can explain that to the patient. And finally, theoretical. We won't be able to improve these models if we're not knowing why they're failing on certain things and what they're doing well on. So the two general approaches that I'm going to summarize quickly are dealing with how we can actually pull some understanding from these models, really divided into either indirect understanding or direct understanding methods. In indirect understanding, we're actually basically trying to figure out what the model's thinking by looking at what types of data it's getting correctly and what type it's getting incorrectly. So the work is more on us to do it, as opposed to the direct approaches, and what they're doing is they're actually approximating interpretable structures from these interpretable black box models, and there's really two strategies for that. Because of the technical difficulties and all that, I think maybe we can actually postpone some of the details of that for later talks, but really these strategies exist and they're starting to pick up a lot of traction over the years. So for the first approach, basically, since I said the work was on us, it turns out that some of the arguments that are proposed are, whenever we're not sure why a model is doing something, some people claim it's our fault. For example, in image recognition, because we know that pixels and color are really important for our own predictions, when we use those as inputs for models and models do well, we can say, well, they used color and pixels in order to do their prediction. But in disease diagnosis, because maybe if we don't know the factors that contribute to a disease, the argument is that, well, therefore you clearly won't know why a model did that either. I'm not really a fan of this kind of this argument, but it really seems to be something that we can work off of, because I myself saw that you can really use the data set in order to infer certain things about the model. For example, one thing I learned was that deep learning models really are obsessed with genders. So they can actually make a lot of predictions just by the gender of names. If you drop out, for example, Liam, which is a male name, with Bianca, or with Helen, it'll tend to actually change its predictions. So at least I'm gaining understanding about the model by changing the data, that maybe it's using gender in order to make a prediction. This one's really cool. So with image recognition, some researchers found that, let's say you see that a model is doing really well at predicting from these pictures that there is a wolf in there. But they found that in the data set, every time there was a wolf, it was snowy outside. So if you really want to understand whether or not the model actually understands what it means to be a wolf, or how it looks like to be a wolf, what you can do is give it a data set instance like this. So give it a new instance with a wolf in a city and see if it gets that correctly. Or another instance would be give it a husky in the snow and see if it gets that correctly as well. So there's some work on that as well. Now, the more interesting work is to have direct ways of understanding models. And the direct ways, one of them is that I was really excited about when it was released, was called LIME. So this is local interpretable models with explanations. Long story short, what it does is that it will predict certain things that the model may be doing in order to develop its predictions. For example, if a model is given the document and it's to predict what topic it falls under, let's say atheism, it'll actually highlight for you some of the words it's looking at in order to decide whether or not the document falls under atheism. So some of those words that are highlighted that may not come up are, for example, owlnet, which may be an indication that the article is about atheism or not. Another very popular thing is attention. So models have been really relying on this very recent mechanism called attention, where it can actually reveal to you parts of the input that it used that may be very relevant for the output. For example, for this task where you're giving a model a picture of a bird and it's supposed to give you a caption for it, for every word in the caption, it'll show you the weight that it put in for parts of the image. So for example, when the caption word was bird, you can see it highlighted bird, because maybe it found the actual part of the bird relevant, okay? Now, other approaches as of 2022, so this is something that just came across a week ago, was you can actually have models generate explanations too. So you can actually ask a model, why did you answer this? So in this case, this was a math question, like Tom has 12 coins in quarters and nickels, gives it a problem, and the model can actually generate an explanation. The limitation of this, of course, is in math, there's usually a one-to-one relationship with a problem and a correct explanation. So it's really just a conversion process. So it is a kind of limited demonstration. I wanted to really get to this point, which is really the paradoxes of explainable AI. And it really started with a huge debate in 2019, where someone brought up the point, and this is Jane and Wallace, that attention really isn't explanation. And I really want to just show this to you guys with a slide here. And it's like this. If I showed you the model's kind of consideration of what it looked at when it predicted that this image is a Siberian Husky, if it outlined that Siberian Husky, you might say, oh, it was really looking at that dog and it predicted Siberian Husky. That's a good explanation. But a team really found something cool in 2020, and that was that they actually perturbed the image a little bit and managed to make the model think it was a transverse flute, whatever that means. And it also highlighted the Husky. So it looks like if you can believe that the model would have used that to get a transverse flute, then you're not really thinking the right way to think that it's looking at that to get a Siberian Husky as well. So then it looks like explanation is not attention really is an explanation, because just highlighting the thing and expecting the human to say, oh, I agree with you, isn't really a good explanation. However, Wygrief in 2019 countered back, and the counter back was also really cool, and said, how often are humans faithful about their explanation? For example, if I ask someone here, why did you buy that shirt? You'll give me an explanation because maybe I liked it, but that might not actually be the reason why you did it. So maybe we're expecting too much of these models as well. And another problem is we're realizing the better that these models are to explain a phenomenon, the worse they are in terms of performing. So there's a trade-off there, and we have to analyze, in the end, it's a philosophical question, what do we want from models? Because if models, we're making their limit be human performance and think exactly how humans think, why are we coming up with AI models in the first place? Maybe we want to make them do something differently than humans, and therefore we might not be able to actually understand how they explain it. So this is actually something that we just need to discuss. I think I have around 5 minutes left where I can summarize the ethical problem. So the ethical problem, which is a huge one, and I don't mean to say 5 minutes because it's less important, but because we're running out of time. In general, the three problems there are systems seem to have a lot of stereotypes that they're exhibiting from the data. We want to look at why that is and what are some ways of debiasing them. Also, something really weird and sci-fi is that it turns out that models are influencing us as much as we're influencing them, which is kind of scary. And I'll give you an example of that. And finally, what are the other dangers in machine learning models that are biased, and what can we actually do about them? So systems being biased, I showed you guys an example of that healthcare problem where you had a model actually be heavily biased in favoring white patients over black ones. There was another one in terms of criminality assessment. So it actually used a questionnaire that was filled by people in jail in order to predict what the chances are that they would return to jail. And it turns out that analysis that was done by researchers afterwards found that was heavily biased and incorrect in predicting that black males would be going back to jail. And it was like extremely wrong in doing so because they did research analysis and found that it turns out that, and in a way we couldn't blame the models because humans were just as bad at predicting that black males would go to jail again. So it turns out that models were mimicking the data that was really copying stereotypes in the wild. So that's a big problem. And then as well, one that was actually taken down quite recently was an Amazon hiring algorithm, which was found to be biased against women. Researchers found that just putting something like women's chess club captain versus chess club captain made the resume have a lower quality for the model in terms of predicting it be a good resume. So there's some serious problems that are happening. And like they're being put under the rug. So Amazon immediately took this down, and it was just a recent op-ed that was released that revealed this happened. So these are some serious issues. I personally worked on co-reference a lot. This one's really cool. If you say to a model, the physician hired the secretary because he was overwhelmed with clients, it'll correctly say that the physician is he, right? It has to the question of this task is to say, who is he, the physician or the secretary? But if I give the model, the physician hired the secretary because she was overwhelmed with clients, it'll think she is the secretary. But the logic shouldn't change. A physician hires a secretary because they're overwhelmed, whether or not they're a girl or a boy. So models are very gender biased as well. And they're also unfair. So in this, I'll gloss over it. It turns out that they're doing more poorly when it comes to predicting, to making predictions on instances that involve females than on males as well. Now, what I did was my theory was that these models actually didn't have common sense. So I actually used counterfactual data augmentation, which we talked about, to give models both versions of a sentence where it's basically seeing that it can't just use names, and it turns out that they actually do really well, and they're discouraged from actually having gender bias. Other cutting edge methods as of the last few months, actually, it turns out that counterfactual data augmentation, this trick that I'm using, only really works with gender really well, and it fails for race, religion, and orientation. One theory I have, and this is just the thing that I'm thinking about recently, is that I think maybe it's because perhaps, and even this is something that's going to be updated maybe in the future, but gender, maybe since if you're just thinking in terms of male or female, it's easy to just counterfactually change the label to the opposite gender. But when it comes to race, religion, orientation, there's a multitude of those. So it's really hard to make a model train for cases where there's more than just a binary label. Dropout as well is something that's being used as debiasing. It's just a method in order to prevent from overfitting. And then as well, something really cool that I came across was noticing that biases are different for different languages. Apparently, when you translate a data set to, for example, French, you'll find that the French annotators will have different biases than English ones. So if we're just training on English data sets, you'll find that you won't capture all of the biases, or you'll overestimate certain biases. So there was a work done by Neviol in 2022 where they measured bias for French data sets, and they found some interesting stuff. Something that's really cool is that there's a method called self-debias, and that seems to be the most successful one. You actually reveal the bias of the model in itself and tell the model to not have that bias, essentially. So you can actually give like language completion. You can give a model, the following text discriminates against people because of their gender. You're basically asking it to be as basically gender biased as ever. And it'll give you a sentence that's extremely gender biased. It'll say something horrible and then tell it not to say that. So you'll scale down the words that it's about to say. That's called self-debiasing. It's like basically me telling you, be as racist as ever and don't ever say that again. And this is actually tending to do really, really well for models. The ethical problem that I was talking about, models influencing us as much as we influence them. I won't give you that demonstration, but there's this really cool thing, I don't know if you guys have heard about recently, called Copilot, where if you just give it a comment of a code, it'll complete the code for you, which is shocking stuff. So to my own students, when I tell them this, they kind of ask me, well then professor, why are you teaching us how to code if this model is gonna do that for us? Which is exactly the fear. It turns out that some of these models are gonna affect the way that we code. And I did a deep dive into this and I wrote an opinion piece as well. And I just summarize this by saying, number one, there's some serious security issues with these kind of models because you can actually prompt them as well. If I write API key, I might be able to find the API key of the data that it's training on. And really there's some security breaches there. It turns out there's some weird performance issues with these kind of models. And finally, the ethical issue that I wanted to highlight was these two phenomenon by psychologists that are really identifying them called automation bias and anchoring bias. It turns out humans tend to trust robots a little bit more than they should. So if I commented, for example, I want to write a tic-tac-toe game and it wrote the code for me, just because it was a robot and I was told that like the machine wrote it for me, I'll trust it and may not test it further, and there'll be some serious problems there if I deploy it in the real world. Anchoring bias is, as I'm writing a text, and this happens all the time, let's say in search engines, if I see a continuation highlighted for me, it'll bias my thinking and I'll actually write my code differently. So that's a huge problem. And finally, because it's black box, we don't know why it wrote something for us. So it's not really pair programming, it's not collaborative, it's really not teaching us how to code, and that's some educational problems with that as well. So, and this is the last slide that I'm really gonna, or the second last slide that I'm gonna talk about, and this is some new work in the field that's saying, what are the actual steps that we need to really take as a community in order to be ethical? The first one is consider the worst case scenario, so perform a pre-mortem. One of the worst case scenarios that happened with Twitter, if you guys have heard about that, was they released a chatbot, and I censored the swear word there of the article, ironically. That was very racist, and that was a really bad scenario that they should have, in retrospect, thought about before they released it. Another thing is to ask the justifications for the researchers that come up with these models. Ask them, are you coming up with this model because you're trying to come up with the state of the art, because everybody else is doing it, because you're trying to make money? These are called high alert negative justifications that we have to be wary of. List the people affected. So I started actually using this data sheet in order to actually answer some questions. Which groups are represented in the training set? Who uses the system and who does it affect? What are the consequences of a false positive or negative? And what are the values, for example? So like, let's consider developing new works under principles like freedom, peace, security, dignity, and respect, justice, equality. But the point is that when you basically are promoting one principle, it might be at the cost of another. And it's not that we're trying to solve, world hunger, but it's to be transparent and say that, for example, if we are prioritizing security in one case, to openly say that equality might be in danger of doing this, to actually be transparent about it when we're releasing these works. And finally, in conclusion, so we see that for the generalizability problem, when they don't really perform well in the real world versus in the data sets, prior work we saw worked on data augmentation and new benchmarks. Current work that I'm really excited about is this human in the loop and never-ending learning idea, as well as looking at models in different domains. For example, we're working together on finance, which is like asset pricing model. So these are constant opportunities to see how these deep learning models are actually doing in other domains. So this is actually a really good way of tackling the generalizability problem. And also for interpretability, we see that a researcher that I'm working with currently is maybe we can actually give these models common sense. And one person that I'm working with, actually we're generating clarifications based on answers, and that might be a big step forward. And finally, in terms of ethics, is to be goal-oriented in terms of ethical design, to clearly outline what our goals are when we develop a model. Is it for security? Is it for equality? And to develop models by that. Other cool new trends and ideas in NLP that I'm coming across that in the future are going to be probably very hot topics that we can talk about later are, for example, storytelling, multilinguality, and psychology-inspired NLP. So I really rushed at the very end to try to get some time in, but hopefully we can start to have a better picture of this question of, is it science or science fiction? Thank you.
Stay here. Thank you very much, Ali, and apologize for
okay.
what occurred with the technical thing. You know, we are an AI research thing, not yet completed.
Exactly.
We are working on that.
Exactly.
Margareta, do you have some questions remotely?
So in the chat there are no questions, but I have a question. First of all, thanks Ali for this very clear presentation, also to a target that is represented by social scientists. So we are less used with the language and also the tools you presented. I have a specific question because you showed the different application of these models in finance, in marketing specifically. And you showed also that these models could refer to machine learning or deep learning. So which model gives the best accuracy? So if I have to manage a large data set of customers, which model I have to apply and it is the most accurate?
That's a really good question. Thank you so much, Margarita. Yeah, you know, it is such a cop-out of an answer to tell you it depends. And I really don't want to say that, but it looks like it really does depend. What I can try to tell you in terms of a productive answer is that it looks like, at least as far as the class of models, transformer architectures, which really are, and I'm going to fast forward back all the way to these giant models that I'm showing you right here. These are all the class of models called transformer architectures. So these are these deep learning models that were these black box models that are just a bunch of layers of nonlinear activation functions, but they have an extra innovation called self-attention. And self-attention was actually an improvement on the attention mechanism, which I talked about, not for the purpose actually of interpretability, but more in terms of training efficiency. So these models actually, because these transformer models are so efficiently trained, they can train on really, really large amounts of text and become experts at some of the nuances of that text. So they'll become really good at just understanding potentially, maybe I'm hyping them up too much, but potentially just what it means to be English or French. Then you can fine tune them on a specific task. So if I trained a transformer model, let's say on a task in terms of predicting a firm's value, on some smaller or some moderate level data set, then I can apply it to that specific task that you personally have in mind, and they seem to be doing the best in terms of accuracy. I personally have some qualms with these because my worry is that they're doing well on accuracy because they're finding some spurious correlations. So they're finding some things that tend to correlate your input with your output and do well in terms of accuracy, but at the cost of generalizability. Right? But if you really are just focused on accuracy, my short answer to you would be transformer architectures, the best of which is essentially the largest one that we have, which is PaLM, the Pathway Language Model by Google.
Okay, thank you very much. There is a question by Leopoldo. I read from the chat. It's a very nice presentation, Ali. One question, could you elaborate a bit on the issue of common sense in the context of NLP?
Absolutely. So I actually had a talk on this. My first talk with SKEMA was all on common sense reasoning. And the reason, maybe you caught it also, maybe it's your pet topic, but it really is mine, because my theory is that actually the hidden solution behind a lot of these issues of generalizability, interpretability, ethical issues is common sense reasoning. It looks like the difference between us and models is that we have this shared key between humans of things that just are true, but things that we don't say, right? We experience things in the real world. We experience, for example, that when Kevin yells at you, Kevin's angry, but we don't say it. Now, because models don't experience this in the data, because we experience this in the real world, they lack this. And because they lack this, they're not generalizable, they can't be interpreted, and they have ethical problems. Because sometimes you can argue common sense helps us from being unethical as well. So common sense still becomes, as of 2018 until now, every conference I go to, it's the hot topic, because it looks like it's the very thing that is antithetical to these models. These models are very data keen, they're very data eager, but common sense is the very thing that's not in data. It's the very unspoken thing. And that's why I personally call it like the dark matter of AI. So how do we endow models with common sense? That's the current work that I'm doing. And it involves, in a short answer, is that maybe you can develop these huge knowledge bases of common sense and have models learn those. So you're kind of, in a way, making those models experience the real world, but with these repositories.
Do you have more questions, Margherita?
No,
No?
not on the chat.
Do
But
we
I
have
invite
questions?
maybe.
Okay, we have a question here, Sam.
You mentioned human in the loop learning.
Mm-hmm.
There I was wondering like how much data you need, right? Like how, yeah. So basically like the models, I guess like you're working, your like anchor point is some pre-trained model that has been trained with like, you know, a lot of data. And
Exactly.
Like, yeah, so how much data?
How much? Okay, so the work, you can't see the screen. Can they see the screen in Paris? Probably not. It's okay. I'll answer it and hopefully they'll interpret it, because this picture that you can't see it either. So the group that I saw that first worked on this is in 2020, and what they did is exactly what you said. They got a pre-training model, and this pre-training model, they had it be fine-tuned on natural language inference, so that's a specific task, and then they gave it batch by batch instances of humans. How much the pre-training data that it learned on, let's say, is in the scales of millions, if not billions of sentences. The batches of those augmented instances by humans were hundreds by hundreds. There is a question of whether or not that's efficient to be able to fine-tune a model every 100 by 100, and they varied that parameter a little bit. Not as much as I think they could have, but yeah.
Also, like, what's the difference from like,
I think,
Does it work?
go ahead, I can hear you.
So how is this different from like regular supervised learning?
Yeah, that's the key. I think the difference between regular supervised learning is that it's not ongoing. The data set has a limit, it has a final instance. This is constantly being updated, and I think it's a subtle difference. It's not that it's not supervised learning. This is exactly supervised learning with labels. But the model is constantly being augmented, or the data set is constantly being augmented, and also adversarially. So it's almost like GANs, but it's not even artificial. It's not a generator. The human is the generator. Yeah.
Can you replace the human with the GAN?
I think you could. The fear, though, is that GANs as generators are just not as adversarial as humans are. That's all. Because the problem with the GAN is also it's very model dependent. The GAN is one model, right? And humans are potentially different generators. And so imagine getting thousands of humans with different sources and different understandings of language to constantly pit against the model. So that's why, yeah.
Maybe a last question, Sam, to René, because we have a few minutes only. René?
Yes. You mentioned medical diagnostics, and then you say, well, you know, we can have a very deep learning model and then go into all the details to arrive at accurate answers. But can we, in a way, make another set of outputs, which will be how all these answers will be translated for a human being with a certain level of knowledge about health, right?
Yeah.
So, in a way, I mean, like the things that a doctor will read will be accurate, given the model, but the thing is, it will translate it into a language or into sentences that the human can understand.
Exactly. I think we can do that, and there is some work doing that, using attention, and not only using attention, but this example that I gave you that unfortunately I didn't have enough time to go into the technical details of Lime, but as you saw what Lime did, which was really cool, was that it had a way of approximating an explanation for a non-technical person, like a doctor. For example, if a model was to predict whether or not a certain disease would occur based on certain factors, it would act, and you know, as you know best, these factors are combined non-linearly for the model. But what Lime does, it approximates the closest linear interpretation of that, and will give the doctor, let's say, 3 of those variables and say it could be very heavily weighted by smoke, the amount that they smoke, their age, and some other factors. And although it's not exactly what the model did, it's as faithful and close as possible. And they did do some very nice theoretical work to show that it really is a good approximation, these linear approximations.
Thank you.
Thank you, Ali. I've been told
Sorry,
that
Ali.
we have
There
two
are
more
two-
questions on the chat. Margherita,
Esatto,
do you
there are
want
two
to
more
read them?
questions. Allora, you say that you mentioned that the use of NLP to analyze 10,000 reports and predict a future value in your talk. So the question is, were these models interpretable and taught us how language can help a prediction? So can tell us if the language can help the prediction in some way?
Good question. So the report, the paper that I read, I believe if you said 10K filings, yes, the 10K filings, they did use approaches that were interpretable. They didn't use deep learning. And I mean, that's the trade-off. I saw there was an opportunity where they could have used deep learning and do a better job potentially, but they didn't. And in fact, they did offer interpretable, at least somewhat interpretable explanations about how those text within the 10K filings related to the firm's performance, specifically because they used approaches that were interpretable. Like, I think I saw a combination of decision trees and SVM, which are all models that you can actually approximate some sort of interpretation or explanation for it, right? So as of now, maybe it was more of a concern for them to be able to explain it versus be able to do really, really well.
Great. There is a final question by Chito. He asks, what are some fundamental differences in the interpretability challenge between NLP and other types of artificial intelligence?
Oh, that's $1 million question. It looks like NLP is particularly struggling with interpretability more than the others. And I wish I had the monitor up, but when it looks like for image or computer vision, the parts of an input are not discrete. What I mean by that is that, for example, a pixel has a very nice interpretation altogether of itself, RGB. There's a scale of what it means for something to be red, green, or blue, and anything in between that, right? There's a difference that you and I understand and can give a model between the difference between something red and something green. We can quantify that. But you tell me, what's the difference between the word cat and dog? The word cat and dog just look like symbols to me. Right? There's no quantifiable difference between the word cat and dog. And how do we actually give a model the understanding of these two differences, right? So for vision, they seem to not struggle so much with interpretability. And that's why you can see these really nice pictures and attention of faces and of highlighted birds. But when it comes to words, it's really, really difficult because this idea of how do we actually understand a word or define a word is something beyond ourselves, let alone for these models. So natural language processing seems to be one of those subfields in AI that particularly struggles with interpretability, just because language is so evolved as this process of AI that we ourselves don't really call a cat because it sounds like the sound cat, right? It's because we are designators of language, and it's really hard to get a model or a machine to do something that we're doing like that.
Alors, il m'appartient de dire au revoir à tout le monde. Donc, je suis désolée d'interrompre ça, mais nous avons déjà dépassé le temps que nous avions. Je vous rappelle que le Centre de ressources et de recherche de Montréal démarre ses activités. Je veux remercier les diplômés qui sont venus se joindre à nous ce matin. C'est très apprécié, puis on espère vous voir souvent. Merci aussi aux employés du Centre. Merci aussi à tous les membres de la communauté qui êtes en ligne. Je vous invite à poursuivre le dialogue. On coupe ça court à la conversation parce qu'on doit libérer plusieurs d'entre vous. Mais je pense qu'Ali va être content de vous répondre si vous lui acheminez vos questions par mail. Si vous les acheminez soit à Margherita, soit à René, ils pourront aussi faire suivre. Merci à Sem, qui sera peut-être notre prochain conférencier, puisque c'est un autre de nos professeurs. Et au plaisir de vous revoir très prochainement. À bientôt.